As objects move in circle, an acceleration always points towards the center. If the acceleration is pointing towards the center, the net force also points towards the center. And therefore it is called centripetal force. The centripetal force points, okay? Centripetal, P points towards the center. Okay? As opposed to centrifugal, where you have an F, and that's feelings, and we keep feelings out of physics, and therefore it is fake. There is no centrifugal force. It's a fake force. It's a feeling force. Centripetal points to the direction that it is happening. Your feelings don't point anywhere. Although sometimes the spinning ride that spins round and round and round gives people's feelings of nausea. Or as you are pressed against the wall, the answer in physics becomes, why are you pressed against the wall? Not just, okay, I'm feeling really pressed against the wall, but why are you pressed against the wall? If all of a sudden, poof, magically, those walls go away, where do you go? As some in the classroom are saying, you go straight. Because what's keeping you from going out is the wall that you're pressed against. And the feeling you have is the wall pushing back on you to keep you in the ride as you're spinning round and round and round and round. So let's look at this diagram. What direction is the net force on this little mass hung from a string as the person is in the ride, so to speak? So what is the direction of the net force on the ball? So a lot of times people want to draw a free body diagram from the previous picture like this, where you have the tension of the person holding it, okay, to the ball, the weight of the earth on the ball, and because it's moving that direction when it's being held, a lot of times people will want to write the free body diagram that way. But you can't label that force. And if you can't label the force, you can't come up with like, okay, this is where maybe you can't label the force does not exist. Just kind of like in Mean Girls, the limit does not exist. Well, if you can't label the force does not exist, is what we look at it. So as you're putting things together, yes, there are going to be, sometimes there are, every now and then when you're drawing free body diagrams, you run the risk of, I missed that. And it's just kind of coming down to looking at the environment that it's in. Okay, we have this, we have this, we have this, we have this. It's forcing us to look at things differently. The drawing good free body diagrams force you to look at everything differently. Okay? So our free body diagram needs to be at least what we can label. Right? We might want to say that there's something here, but we can't label it, so we have to eliminate it. Doesn't mean that you can't have it in the back of your mind. I'm like, I think it might be there, but I'm going to investigate to see if there is something there, or is my original thought incorrect? And that's okay, especially when we're first starting out and learning a lot of this. And I think that's the problem we come with, is becoming okay with like original thoughts being incorrect. It's okay. It's a very natural thing to happen in physics. Okay? That's our remember our pre-test that we took showed there's a lot of things that we see and think about as our natural world around us is doing one thing, but it's obviously we're seeing and thinking about it differently, or we have some misconceptions. And coming to head and being okay, like, I'm wrong. It's okay. I've learned to say it lots of times. I'm also married, so it just goes hand in hand. But that's just how life goes. I'm also a father, so I'm wrong a lot because, well, they're different. So we eliminate it. Might be wrong, but so this is just kind of like, all right, this is a base what I have. Now, I can eliminate that angle part by drawing two other parts of the tension. I can put the X and a Y component to that tension. Okay? Can kind of break it down further because that angle thing, it's not going to help me understand why, in the little picture up here, why that is pushing back at our face. Okay? Sometimes it's harder to see or envision it. So we use the blue dotted lines to identify the kind of the X and Y's. Get it just in two planes instead of this at an angle thing. Sometimes it's easier to see it that way. And so that's why we eliminate the tension of the string on the ball. The vertical line would be the tension of the string on the ball in the Y direction. Here we have the string on the ball in the X direction. Now ultimately, when we put it all together now, we can see where the force is actually pointing. To the center of the circle as it's going around and around and around, and that would be the tension in the X direction as it would point towards the center. What just boggles our mind, then why is it going back towards us? Okay, remember inertia? An object wants to stay going the same direction, right? Why, when you have the fuzzy dice on your rear view mirror, when you hit the accelerator really hard, does it go back? it wants to stay put. Same thing with the ball on the string. It wants to stay put. But it's constantly moving, so it's constantly trying to stay put. And it stays in that same location. Lots and lots and lots of times around. Now, why do you get slammed to the side of the thing? You want to stay put and you want to exit. But what's really nice about those things is that those walls are there for you to stay in there. All of a sudden, they magically poof go away, you go straight flying out in a direction. Same thing that we had used as an analogy before. What happens if poof, all of a sudden the sun goes away? What direction do the planets go? Same analogy. They go off into space at a straight line. But this here is pointing. And now we can see, we're like, but what about this one over here? It wouldn't be there anymore, would it? It's there because of inertia, wanting to maintain its location. Kind of putting some things back in because the force is pointing to the center. Force divided by mass tells us the acceleration is also pointing in that same direction. Because mass is scalar, force is a vector, it's going to shove itself back or show that it's pointing also in the same direction. That's one of the nice things about force and acceleration is usually they're going hand in hand. Where the force is, the acceleration is as well. So now when we kind of look at the free body diagram again, now we answer the question, which force is the net force? Well, in all reality, technically they're all the net force, right? But which one shows us that there is any? Is there a net force in the y direction? Yes, it's just 0, right? So we're kind of like, no, there's not one. There's only one in the x, and that's our tension. So that's what allows us to kind of get things going there in that manner. And again, the acceleration is also pointing there as well.